Section 10.8, Taylor series. Our final section, I should say, of Chapter 10. I've written some famous Taylor series right here. We'll visit these later on in the section. So, what's the idea of the section? There's two main ideas, which is, in the last section, in section 10.7, we learned how to approximate functions with polynomials. So we had the idea of Taylor polynomials. So let me bring this back here. Here's our definition of Taylor polynomials. T sub n, the nth Taylor polynomial of f centered at x equal a. Here's the definition. Here's how we define the Taylor polynomial. And so these are polynomials that approximate our function. It's generalizing the notion of linear approximation from way back in Calculus 1. So instead of just approximating our function with a straight line, we could approximate with a parabola or a cubic polynomial or stuff like that. So this is one notion. In the last section, we approximate function of polynomials. In section 10.6 on power series, we talked about how power series generalize polynomials. That, in some sense, a power series is an infinite polynomial. So guess what? You should have some, if this is a live class, I'd be asking, what do you think we're going to do now? Well, we're going to take our Taylor polynomials from section 10.6 and turn them into power series. So here is, once again, our definition of Taylor polynomial. And so we are going to have the definition of the Taylor series. If f is infinitely differentiable at x is equal to c, then the Taylor series for f of x centered at c is the power series. T of x is f of c plus f prime of c times x minus c plus f double prime of c divided by 2 factorial times x minus c squared plus dot 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 is the sum from 0 to infinity of the nth derivative of f evaluated at c divided by n factorial times x minus c to the n. So a comparison between these two definitions here shows that these are exactly the same. I guess here we're using A instead of using C. But here we're stopping at some fixed value of n. We're only going out to order n. Here we're turning it, so I should say this previous one, this is a polynomial. But this one is going all the way out. This one is going all the way out to, going out to infinity. We're turning this into a power series. Okay, so this is what we're going to be doing in this section. Throughout most of the questions, well, maybe not most, but many of the questions are going to be, here's a function, find the Taylor series for it. And those questions are going to feel very, 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 very similar to the Taylor polynomials. If you can do the questions from section 10.7 on find a general form of the Taylor polynomial t sub n for a given function, you should be able to find Taylor series. Just like we have Maclaurin polynomials, we also have Maclaurin series. So Maclaurin series is just going to be the Taylor series centered at c is equal to 0. Most of our well-known formulas are going to be Maclaurin series. Last thing to point out in this in this video is going to be Theorem 1 on Taylor series expansion. So we should be thinking about, if we have this Taylor series, this power series that's generalizing our Taylor polynomials. Our Taylor polynomials are approximating our function. When we turn it into a power series, does it still approximate our function? And so here's this Theorem 1 on Taylor series expansion answers that question for us. So if f of x is represented by a power series centered at c in an interval that is absolute value x minus c is less than r, so there's the center of our series. Here's our radius of convergence for our power series. Remember all those concepts from section 10.6. and we want our radius to be strictly greater than 0, then that power series is the Taylor series, exactly this. So what does this do here? This is going to tell us that that the only power series that could represent our function, if we do have a power series that exactly matches our function on some interval, it has to be the Taylor series. And so this is actually something that we will prove together here. So let's suppose that f of x is represented by a power series centered at x is equal to c, and so it's on the interval c minus r to c plus r, and we want the radius of convergence to be strictly positive. So f of x is the sum from n from 0 to infinity of a sub n times x minus c to the n. So writing out the first several terms, that's a naught plus a1 times x minus c plus a2 times x minus c squared plus dot dot dot. Let's go ahead and compute derivatives of this. So remember back in our power series section, section 10.6, we said we're allowed to differentiate power series term by term. Let's do that. So f prime of x is going to be, so the derivative of this is 1. Well, let me start off with just the regular function here. And that derivative wasn't going to be 1, it was going to be 0. I'll fix that. So a naught plus a1 times x minus c plus a2 times x minus c squared plus a3 times x minus c cubed plus a4 times x minus c to the fourth. F prime of x, okay, a naught, that's going to go away. When we take the derivative of this term, we'll get a1. When we take the derivative of this term, we'll get 2 times a2 times x minus c. I'm using the chain rule to do that derivative. Bring down this 3 times a3, and we still have x minus c squared. Bring down that 4 times a4 times x minus c to the fourth plus 5a5 times x minus c to the, oops, that should have been cubed there because that 4 becomes a 3. When we take second derivatives, this a1, that goes away. The derivative of this term is going to be 2a2. The derivative of this term is going to be 3 times 2, a3 times x minus c. The derivative of this term is going to be 4 times 3 times a4 times x minus c squared plus dot dot dot. Maybe one more, just kind of see how this is going here. So that's a constant, that derivative is 0. Derivative of this is just 3 times 2 a3 plus 4 times 3 times 2 a4 times x minus c plus dot dot dot. So we can calculate what's going on here. So what's our general formula? So looking at this, our general formula, the kth derivative is going to be, it's going to start off with k factorial. So note that this is 2 is 2 factorial, 3 times 2 is 3 factorial. So the kth derivative starts off with the k factorial times the first derivative matches up with a1, the second derivative matches up with a2, the third derivative matches up with a3. So k factorial times a plus k plus, this is going to be 2 times 3 times 4, 2 times 3, 2. So multiply together, 2 times 3 times 4 times dot 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 times k plus 1 times ak plus 1 times x minus c plus dot dot dot. There would be higher and higher powers of x minus c in each one of these terms. Well, what happens when we plug in? What happens when we plug in c in for x here? We get k factorial times ak plus something, who cares what, because we're going to have plus something times 0, plus something, the next term would have an x minus c, a c minus c, a 0 squared plus 0 cubed plus dot dot dot. So this is just going to be k factorial times a sub k. So that's what's going on here. F, the kth derivative of f evaluate c as k factorial times a sub k. Well, solving this for a sub k gives us the kth derivative at c divided by k factorial. And so this matches our Taylor series. So this exactly matches this right here. The coefficient, so a sub k, this is the coefficient of x minus c to the k. And so everything matches up here. So this says that, yes, we're on the right track. So this finishes our proof of Theorem 1. We'll have another theorem that will argue that, tell us more about convergence. But first, in the next video, we'll do an example of calculating out a Taylor series.